should be in pretty good shape. Okay, so I'm gonna try and get through maybe the first page so we can talk about a lot of the vocabulary to kind of get this sinking in. 6.2, you do need to get that done. We will correct that tomorrow at the beginning of class. We're gonna try and get through 6.3 maybe by the end of tomorrow. That way you can work on it on Thursday night. We'll take some more questions on Friday. And we'll see when we make that due. Vectors are really important. They have a lot of really cool applications. Hopefully we'll get to take a look at some of them. Again, if you're going into science or engineering, physics or something like that, vectors are really, really important, okay? So we want to make sure that we've got a basic understanding of what's going on, and we kind of need to build a vocabulary here. So how many of you have seen and heard of vectors before? Raise your hand. Okay, excellent. If I go too fast or something like that, just holler. If we use a slightly different vocabulary or notation, let me know and we'll get used to it and just make sure everything matches up. Okay, this textbook doesn't use this word very often, but I want to make sure we're clear on what this is because you're going to see this word quite a bit. So the word scalar is a quantity that measures only magnitude. It measures how big something is. Okay? So one way that we could say this is that it's just a plain old number. Okay? So something like 5 pounds. If we said 3 miles. If we just said 4.2. Just plain old numbers. Those are examples of scalars. Okay? And we use the word scalar specifically when we're talking about vectors to differentiate a couple things. And we also see it when we deal with something called a matrix. Okay? And if you've heard of a matrix before, great. If not, we'll deal with some matrices before we're done with it. Yes. Okay? All right? So let's talk about what a vector is and how it differs from a scalar and why we need these two vocabulary words. So a vector is a quantity that measures magnitude, how big something is, and it also measures direction. So it's a plain old number with a direction. Plain old number is a scalar. If you put a direction to it, then we've got what we call a vector. So if I said 5 pounds, so let's say I was pulling with a 5-pound force to the east. That works. If I said 3 miles, let's say we do 3 miles per hour, okay, at 80 degrees. Okay, so kind of like that airplane example that we had before. And if I said 4.2 at angle of 7 degrees with the horizontal. So as long as I give a direction to it, I've got a magnitude, I've got how big something is, and we normally use forces like pounds or newtons or different things like that, or we use speeds in order to do that, so miles per hour or something, okay, and give it a direction, then we've got something that we call a vector, okay? And we can represent a vector geometrically, so it can be represented by a directed line segment. How long the line segment is, okay, so the length of that line segment, that represents the magnitude. Magnitude represents how big it is. So the larger the line, the larger the vector, okay, the larger the magnitude, okay, and the angle represents the direction. And we normally like to standardize things and make sure everybody's on the same page and measures things. Trouble? Okay. Measures things the same way, has the same measurement for angles and stuff like that. So we're going to standardize this just a little bit. So we're going to draw a vector, and this vector is going to go from point A to point B. And point A is 0, 0, happens to be the origin, and point B is 3, 4. And there are lots of different ways that we can indicate or that we denote a vector. So if I have vector AB, sometimes we'll put this little line over the top of it. It's a little arrow. It's a little directed line segment. You can tell what direction it's going. Sometimes we use script letters. Okay, so I've bolded these and kind of italicized them. Sometimes we use the same type of script letters and we'll put the little vector arrows over the top of them. And then occasionally we'll just use a capital script bolded letter and we'll say this is a vector. So we'll say vector C or vector D. Okay, so you see them written lots of different ways. You just want to make sure you're clear on whether or not we're working with a vector or a scalar. So let's take a look at this one right here. This one starts at 0, 0, so here's A, and it ends at 3, 4, so over 3 and up 4, so I'm right there. So I'll put B right there. And we want to indicate the direction here, so it starts at 0, 0 and goes to 3, 4, so we draw it this long, and we put an arrow on the end. So it's kind of indicating it's this big and it's heading off in this direction. So more vocabulary here. Okay, the initial point is the starting point. The terminal point is the ending point. And the magnitude is the length of the vector. It's how long it is. And when we say the magnitude, I mean, we could say the word magnitude all the time, and we do that quite often, okay? But we also denote it a couple of different ways, okay? If we put what look like absolute value bars on it, or double absolute value bars, this is basically asking a question. It's saying, how long is vector AB? Tell me what the magnitude of vector AB is. So if you think about it, if all it's asking for is the magnitude is just how long, so it's a scalar. Doesn't necessarily have a direction on it, okay? So if we say magnitude, we only want that piece of information, just how long it is, okay? And you might want to think about how we'd actually find something like this, because I'll ask this a little bit later on. Okay, and occasionally we'll use kind of informal terminology to talk about these. We'll talk about the tip and the tail of the vector. So the tip is the end point. Where does it end? And the tail is the starting point. So the tail is the initial point and the tip is the terminal point. And then we've got something called a direction angle. And a direction angle is an angle that tells us which direction this vector is headed. So when we talk about a direction angle, it's always measured from standard position. So we just got done looking at an example where we were talking about navigation, where they measure things a little bit differently. Okay, so we need to make sure we keep track of that. When we're talking about the direction angle for a vector, we're normally going to put it on an XY plane. So we're always going to measure from standard positions. So on this one, the direction angle would be this angle right there. Any questions? Okay. So let's do something really quickly. Let's figure out what the magnitude is. So if I wanted to figure out the magnitude of vector AB, I want to know how long this is. We could use the distance formula, okay, because we've got the ending point and the starting point. So we could do d equals big square root x2 minus x1 quantity squared, y2 minus y1 quantity squared. We could do that. Or is there something that might be a little bit easier? What's the distance formula based on? What? Slope, kind of. The Pythagorean theorem. It's based on the Pythagorean theorem. So if I know how far I went this way, and if I know how far I went this way, which is pretty easy to figure out on this one, we started out at 0, 0, and we went over to 3, so that's 3. We went up 4, okay? So this distance right here is 4. So the magnitude on this one would be, I'd have to take the square root, right? So this would be 3 squared plus 4 squared. So the magnitude of AB is square root of 25, so that's going to be 5. So lo and behold, I mean, I did this on purpose, so it was a relatively easy example. I've got a 3, 4, 5 triangle, right? Okay, what if I wanted the direction angle on this? What if I wanted to know what is that angle right there measured from standard position? Alpha, or in this case I labeled it as theta. Okay, I want to find that. How would I do that? You could use the sine, so we could do the opposite over the hypotenuse and then use sine inverse. That would be good. Okay, I could also do cosine. I could do 3 over 5 and then do cosine inverse. Or, I mean, really, didn't we know these two, the 3 and the 4, didn't we know those first? And this one happens to work out to be a nice number like 5, but what if it worked out to be 5.2317? Yeah, probably tangent is going to be our better bet. So the tangent of theta is going to be equal to 4, this vertical part over that horizontal part. So then I'm going to get theta equals tangent inverse 4/3. Am I expecting an angle that's bigger than 45 or less than 45? Bigger than 45 or less than 45? I mean, some of you already have the answer. It should be pretty easy now, right? The answer's bigger. Can somebody tell me why we expect it to be bigger? Why do I expect that angle to be bigger than 45 based on the size of these two sides in particular? Okay, because the ratio there is bigger than 1. The opposite side is bigger than the adjacent side, so this is going to be a bigger angle, okay, than that one up there. Okay, and when you do that, roughly what is that angle there? 53.13. So there's our direction angle. Okay? Any questions? Okay, we've actually covered a huge amount of the section just by looking at that. The only thing that I'd caution you about is I made this example very easy so that it would work out with nice numbers, and this direction angle is in the first quadrant. If it was in the second quadrant or the third quadrant or the fourth quadrant, it might be a little bit more difficult to figure out what the direction angle is. Okay? Tangent inverse is going to give us a nice positive answer in quadrant 1, which is where this is. If it was in another quadrant, you might want to think about how we'd actually do that. Okay, are there any questions? Okay, we're going to pick up right here next time. Can anybody tell me how you'd make sure that two vectors are in fact equal? They'd have to have the same magnitude, exact same magnitude, and direction. They'd have to be heading the same direction. So we'll pick up there next time. Thank you very much.